Okay, is this an alternating series? So we have a -1 to the n. That's strictly alternating. Alternating. What we call the bn's, so that's everything but the negative part. So bn is in this case 6 over n to the 1.2. Those are greater than 0. So I'm testing the alternating series test has 3 conditions you got to meet. Is it strictly alternating? Are the, aside from the alternating part, are the rest of the sequence, are they positive? And then the next thing is the limit 0 without the negative? So as n goes to infinity, we want to know what's the limit of 6 over n to the 1.2. And that limit from our previous experience in math is 0. So check, check, check. This converges according to the alternating series theorem. Now, alternating series theorem only tells us that it converges or not. It doesn't tell us what it converges to. However, it does offer a hint about the remainders. So the remainder is when you stop some partial sum. So if you do a partial sum n, the difference between the actual sum, the infinite sum, and wherever we stop, that's called the remainder. And according to the alternating series remainder theorem, that remainder, that actual error, is always less than or equal to the next thing you tried to add, which would be bn plus 1. Our bn plus 1 would be 6 over n plus 1 to the power 1.2. And we want that right there, that error, to be less than 1/100th. All right, I'm just writing that as a fraction instead. So we can solve this. Everything's positive, so I can do some cross multiplication. So I'm going to multiply the 100 to one side. So that's going to give me 600 is less than n plus 1 to the power 1.2. If I just take the 1.2th root of each side, it's a thing. Then I now over here have just an n plus 1, and then I can subtract this 1 over to the other side. So this value right here is going to be less than n, or I could say n should be greater than that 1.2 root of 600, then minus 1. Calculator, let's see what that number is, and we'll test and see if that's reasonable. And calculator. Just clear this one, we're done with that. All right, so let's see, easier than the root button, I'm just going to raise 600 to the power 1 over 1.2. And then subtract 1 from that. So I get n should be bigger than 205.597. So I would say n should be about 206. Now we have to test to see if that's reasonable. So I think that n should be greater than or equal to 206. So let's look at the 206th partial sum and the 207th partial sum and see if they are indeed about 100th apart. So I'm going to create another sum formula. S of x equals the sum as n goes from 1 to x of -1 raised to the power, and this an n plus 1, it was just an n, and then we have 6 over that. So raised to the power n times 6 divided by n raised to the power 1.2. And now I want to check out what is the 206th sum. So S of 206 And I want to compare that to the next one, S of 207. And what I should expect is they are the same to the nearest hundredth. Let's see. Yeah, they are less than 100th apart. 0.337 versus 347. So we're just under 100th apart there. Double check if you're not sure about that. S of 207 minus S of 206 gives me 0.0099. And again, these partial sums repeatedly jump back and forth over their limit. They oscillate about the limit. So the actual limit is in between those two somewhere. So we are closer than 1/100th for sure for the actual sum. Would 205 have gotten us there? Maybe. There's a little bit of wiggle room in that, because notice my inequality has a couple of steps in it. I have a less than here, and I have another less than there. So the actual error is less than in between there. Okay, not too bad.